After seeing some of the theory and the background to using the first principles, the difference quotient, in order to determine the gradient function for a given function, now we're going to go through a little example and to kind of get your feet wet with this. So when we do something like this, we're going to take f prime of x, which is the notation for the derivative, and this is the limit of this function, f of x plus h minus f of x. I guess we can use a, which is the specific value of x, which in this case is 2, as h approaches 0. Remember that the denominator was just x plus h minus x, and then of course the x is just canceled, so that's why we're just left with h. I'm going to need some room here, so I'm going to put my equal sign over here. So what we're going to do is we're going to substitute in x plus h, and personally I prefer to substitute in x plus h and do all the simplification first. So I'm going to put in x plus h, substitute x plus h in for x in wherever the x appears. So this is all of this is f of x plus h, all of this. And then we're going to subtract f of x itself, which is just the function. And we're going to have to put this in brackets because it's subtraction. And this is going to go all over. I want to keep things neat. That's going to go all over h. So what we can do now is we need to expand out x plus h cubed. We can use Pascal's triangle for that. So we're going to have x cubed plus 3 x squared h plus 3 x h squared plus h cubed. And then I'll do the expanding all at the same time, just to kind of keep things uniform. Sometimes people put square brackets on this last part, the f of x part, but I'll just leave round brackets there for now. Write that 2. This is all over h. And I prefer that you have a horizontal line here. I know it takes more space in your notebooks, but I prefer that as opposed to having all this with a division like this at the end. It just, to me, it just is more precise with the notation. Okay, so please don't just put your over h at the end of the line. I know it uses less space in your notebook, but please do it this way. So I'll expand this in now. So I'll get 2x cubed plus 6x squared h plus 6x h squared plus 2h cubed. Then I'll have plus 3x plus 3h minus 4 minus 2x cubed minus 3x plus 4. Again, all over h. And then we'll see that we can simplify things down. And so we'll have, well, this 2x cubed. We'll cancel with this 2x cubed. This positive 4 cancels with this negative 4. And this plus 3x cancels with that negative 3x. So effectively, the whole minus f of x part just disappears anyways. However, with strict notation, you need to have it in there. I know a lot of people just kind of don't put it in there. They use all kinds of shortcuts. They don't put that last bit in, and then they just cancel out everything else because they know the secret. Oh, sorry, and I apologize profusely here. We need to have this limit as h approaches 0 in every line. So that goes in here. I would be remiss if I were to leave that out. So that has to be in there until you substitute the h in. Okay, so it still is limit as h approaches 0. This is still effectively, the difference quotient is still actually just calculating the average rate of change. Well, when we use the limit definition, then yes, as h approaches 0, then it does actually give you the gradient of the tangent at that point. Now, we've done all this simplification here, so we're left with 6x squared h plus 6x h squared plus 2h cubed plus 3h. And that's all over h. Now at this stage, you have to be very aware. So this is the step right here, even though that golden star doesn't really stand out very well. You have to make sure that you have an h in every term in the numerator at this point. If you don't, go back and look at it again, because there's something wrong. You have to have an h in every step. And the reason why we do that, or we need that, is because we're going to factor that h out to leave us with 6x squared plus 6xh plus 2h squared plus 3 all over h. That's an h here, sorry. And then we can simplify these h's. We still have the limit notation because we haven't substituted that h equals 0 yet. And that now, because we've simplified that h in the denominator, now we have, and I'm just going to move things around in the numerator a little bit. Now we have just a polynomial. We've got rid of that denominator. Now is where we substitute in 0. And when that happens, and the reason, of course, why I moved that 6xh term and the 2h squared term to the end is because they just disappear. So we're left with 6x squared plus 3. That's just a plus sign here. So this then is the gradient function of the original function that we were given. I can draw a 6 properly, and that's supposed to be a bracket. Okay. Now, if we wanted to find the gradient to that original function at any point along the way, we can substitute in 0, for example. And we get 3. We can substitute in -2. So we get -2 times, or -2 squared. So we get 4, 24, 27. So the gradient of the tangent, and i.e. the gradient of the curve, f of x, when x equals 0 is 3. The gradient of that function that was given in the beginning of the example, when x equals -2, is 27. Okay, so anywhere along the curve, you can substitute values into x, in for x of the gradient function, and you'll get the gradient of the original function at those x values. Okay, and that original function was 2x cubed plus 3x minus 4. Okay, so that's how we would work through the difference quotient, work through the first principles definition of finding a derivative, and this is how it would be used in order to determine gradients at different points along the curve. So thanks for watching, and we'll see you in class.